Alright guys, so for number 12, it will be a sort of vector problem. So, definitely not our favorite, but you gotta do what you gotta do. So, two lines L1 and L2, which are shown here and here, intersect at point P right there. Point A, which has coordinates of 2t, 8, and 3, as shown right here, where, and this might be important down the road, the IB, whenever they give us something, it's probably because it's relevant, where t is greater than 0, lies on L2. This is shown in the following diagram. Now, first things first, just a quick reminder, don't freak out. If you have a point with 3 coordinates, that means that instead of dealing with an xy plane, you're dealing with an xyz. So you probably have something that looks kind of crazy with a z value going up like that. Okay, so it does enter like a more 3D-ish sort of plane. But, I mean, especially for vectors, this is something that we have to work around with quite a bit. So, they also tell us that the acute angle between the two lines is pi divided by 3. This is also a piece of information we have to go over. When you talk about angles, you usually have 3 types, or at least in this context. You have the acute angle, you have the right angle, and you have the obtuse angle. The acute angle is any angle that is less than 90 degrees. The right angle is any angle that is exactly equal to 90 degrees, and the obtuse angle, you guessed it, is anything greater than 90 degrees. So if we're talking about the acute angle, instead of being the one that I'm putting in pink, okay, it would be the one that I'm putting in red. Okay, so that angle in red would be pi divided by 3. Now, the other thing that we do have to go over is that you can express degrees, right, or an angle, right? Degrees, yeah, sure. So you can express an angle in 2 different ways. You can put it in degrees, or you can put it in radians. Okay, so this is actually the first thing that I'm really going to go over and hit hard. When we talk about degrees, it's like putting 90 degrees, 180 degrees, stuff like that, okay? When we talk about radians, it's it's like changing units. Okay, it's as if meters was in meters, as if meters was in meters. It's as if degrees were in meters and radians were in, I don't know, like kilometers. Okay, I'm just making it up. But point is, they're expressing the same thing, just that in different units. Okay, so degrees is a way to express angles. Radians is also a way to express angles. Okay, and one of the things that people have trouble understanding is how to understand what pi divided by 3 is as an angle. So if your angle, so your angle equals, in this case, pi over 3 radians. How do you know it? How do you know it's radians? It's radians because you have a pi inside of it, quite literally. Now, unfortunately for you, especially since you're HL and you're watching this video, you do have to memorize and understand the unit circle. The unit circle helps you like sort of transform all these angles and radians and stuff into a more accessible sort of like piece of information. See? So once you memorize the unit circle and you look for pi over 3 on it, you should find it right there on the 60 degrees over here. And so let me just draw the unit circle over here because it will be relevant in just a moment. The unit circle goes like this, goes like that. So this will be x, this will be y. And my pi over 3, right, is actually right there. Boom. So right here, you have the famous pi over 3. Okay. Right, that is a little bit of a small drawing, but point is, this is for pi over 3 radians. Okay. And you also know that it lies on the point. So right there, you have the point 1/2, comma, whoops, 1/2, comma, square root 3 divided by 2. Square root 3 divided by 2, correct? Yes, square root 3 divided by 2. Yeah, so we identified where it is in my unit circle. Technically, if you memorize that, you also know that this is the same as 60 degrees, okay? But that is not the most relevant part here. The most relevant part is the point in which it lies on, okay? Now, I'm not gonna tell you exactly why, but you will figure out in like probably like 5 more minutes. Okay, so it's super relevant to understand where this angle lies on the unit circle in order for you to find, okay, in order for you to find which point it's on. Okay, that's like the main idea I want to transmit to you. You will see it in action in a second. So the direction of vector L1 is this guy here. All right, and they also tell you that PA, so basically the direction of P to A, right, is this right there, right? And with all that information, we somehow need to show that 4t equals blah, 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 okay? Now, this honestly has more to do with understanding the formulas that you have and seeing how you can get t from there. Now, before we jump into it, I do want to give you a quick tip that you can use for exercises like these. Whenever you have show that, then that's telling you that this right here is true. This is a fact. 4t does equal square root of 10t squared plus 12t plus 18. Why is this worth mentioning? It's worth mentioning because for part B, you do need part A, but really, for finding the value of t, you can just solve this equation there. So, if you realize that you have the buzzword show that in the question, okay, and you're having a lot of trouble, well, showing that, you can use it as factual information. See? So what I'm saying is that right here, right now, if I wanted to, or if I was low on time and stuff like that, I could completely skip part A. Yes, I do miss out on 4 points, but I have the chance of earning 4 points by finding the value of t by what I have in the pink rectangle. Okay, so whenever you have show that, just keep in mind, dude, you can skip that part and just move on, like literally, okay? So in case you're low on time, in case you're having trouble solving it, etc., know that that is something you can do. Right, so that is more of a test taking skill or strategy I wanted to show you. But for now, coming back to the actual exercise, how the heck can we show that? So, really what you should do for this sort of exercise is that once you identify that you are dealing with vectors, open up your formula booklet and see what you have for vectors. What are your tools? What can you play around with? Let's see. And so this is why what I always talk about in almost all of my videos, you guys. The formula booklet is going to save you. It's literally going to save you. You have to be familiar with it. Now notice, I'm saying you have to be familiar with it. I'm not saying you have to memorize it. It's very different. Point is, once you read the word vector, you should immediately be thinking, I know that there's a couple vector formulas in there. Okay, maybe you don't recall exactly what they are, maybe you don't remember perfectly how they work, but you do have to know that they're in there. Okay, so the formula booklet is huge once you can identify just sort of vaguely, like, I know I have a formula for that. See, I know that this angle that they're giving me is actually relevant for formulas. Like, that's the kind of thing we want to reach, we want to be able to do. So once you do that, well, you scroll all the way down and it's going to be in geometry and trigonometry. So we go to page 7 and bada bim, bada boom, now we're getting somewhere. Up here, there is the impossible trigonometry stuff that we're just not going to go over because why would we? No one likes trigonometry, but we will go over, magnitude of a vector. This seems kind of relevant. Scalar product. This seems kind of relevant. Angle between two vectors. Well, you already have it, but it might seem relevant. Who knows? Vector equation of a straight line, da 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 da. There's a bunch of stuff here. Okay, it does get kind of wild. I guess you can use more than one equation here, but the approach that I will suggest has to do with these three initially. Okay, so these three initially, you might not see it right away how they're useful. So that has to do with understanding how these equations relate with each other. Okay, the first thing that you can sort of establish, okay, is that this one up here, okay, the v with the absolute value. The absolute value is the, like the walls that is in between it, right? So the magnitude of a vector, the absolute value of v, also shows up here and here. So, you can use this. I'm going to put names to them, right? So equation number 1, equation number 2, and equation number 3. Okay, so you can use equation number 1 to fill in better equation number 3, right? Now, for equation number 3, you also have v times w. And so, look at that. Isn't this just fine and dandy? You have VW right there as well. So you can also use equation number 2, right, to plug all of this stuff in, basically, right there. And now you might be thinking, okay, yes, that's how the formulas relate to each other, but how can you see that that's what you're supposed to do? And here is where the angle turns out to be a big hint. So the IB, this is the thing, the IB pretty much never gives you something that you won't use. Okay, even t being greater than 0 can be relevant here. Okay, so because they gave us an angle, you should have identified, in the formula booklet, I know there's a bunch of formulas, and one of them has the angle. So if here's my angle, well, I probably have to use it. So if you try to use it, well, what do you need to fill in? You have to fill in what's in pink, and for that you need to use the first equation, and you have to fill in what's on the left, and for that you can use the second equation. So that is our game plan. That is what we're going to do bit by bit. So let's start with what's in pink. So what's in pink is the magnitude of a vector. So let's get the magnitude of both of our vectors. The magnitude of L1, right? So I'm just going to put magnitude L1, okay? Magnitude L1, following the formula booklet, basically says you want to square root, your first value from top to bottom, see? Then you want to add it to this, yes, sorry, I'm explaining myself not the best. So you want to square root, okay, the square of your first value plus the square of your second value plus the square of your third value. Okay, that is what you're going to be doing. So how does that look in action? We will have, well, the square root of my first value, so this 1, right, squared, plus this 1 squared, plus this last one squared. So L1, or magnitude of L1, I should say, ends up being simply square root of 2, because 1 times 1 gives 1, plus 1 times 1 gives 1, because 1 plus 1, 2, right? So the magnitude of L1 is just going to be 2. Now, the magnitude of PA, okay, so the magnitude, it's really just the magnitude of L2, see? For me, it's a little bit more intuitive if I leave it as magnitude of L2, okay? So, whatever, to each their own. So magnitude of L2 is going to be the same idea. So it's going to be the square root of your first term, so the 2t squared, plus the second term, which is a 0, squared, plus the last term, which is 3 plus t squared. So the magnitude of this second term is going to be, this first term is going to end up as, well, let's see, it's going to be 4 2 squared plus 0 plus 3 plus t times 3 plus t, right? So 3 plus t, you're going to end up with plus 9 plus 3t plus 3t plus t squared. See? So, in other words, you end up with, so 5t squared plus 6t plus 9. So 5t squared plus 6t plus 9. So here with what I'm putting in, let's say blue, is the magnitude of L2 and the magnitude of L1. So now I'm one step closer to being able to use this third formula. See? Now for the third formula, I also mentioned you do need stuff from the second one. Okay, you do need that whole stuff in order to plug it in right here. See? So what the heck even is that? Well, let's take a moment and observe. So the v times the w, what it's doing, right, is that you're basically multiplying this guy times this guy. See, that's what's happening there. Plus this guy times this guy, which is what's happening there, plus this guy times this guy, which is what's happening there. Okay, so really you're just multiplying all of them like in a row, or so to say. So Basically just L1 like really bolded, right? So L1 really bolded times L2 really bolded has to equal uh 1 times 2t plus 1 times 0 plus 0 times 3 plus t. So there's a parentheses right there. Well, this is 1 times 0, so it's 0. This is 0 times something, so it's 0. Really, you're going to end up with the bolded L1 times the bolded L2. That is a 1. Bolded L1 times bolded L2 is just going to be 1 times 2t, so 2t. And now, ladies and gentlemen, we can finally go ahead and try to plug everything into the third formula, the last one. See? So with the third formula, well, clearly I'm running out of space, so I'll do it. There's a lot of space up here. Nice. So this last formula is the L1 bolded times the L2 bolded equals the absolute value of L1 times the absolute value of L2, ¿cierto? Times cosine of theta. And what's cosine of theta? The angle between V and W, which is actually what they give us right here. The acute angle between the two lines is pi divided by 3. So really, well, this is the equation, right? Now let's go ahead and plug in. So the bolded ones, we figured out that it was just 2t, right? So for the bolded ones, we can put 2t equals the magnitude of L1, which we found was square root 2, times the magnitude of L2, which we found was that whole thing. So square root of 5t squared plus 6t plus 9, okay? Times cosine theta. Now we're talking about cosine, and this is in radians, correct? Cosine of p divided by 3, see? Now we're almost ready to just sort of plug and chug and see what happens. What's annoying us the most right now is cosine divided by 3. This term right here is hella annoying, and to get around it, you need to be familiar with the unit circle. So this is why I presented the unit circle earlier. It's because once you memorize, because you are an HL, so this is one of the few things you do have to memorize or find a way to remember, or etc. Once you realize that the angle pi divided by 3 in radians, or 60 degrees, has the points 1/2 and square root 3 divided by 2, then that immediately allows you to put this cosine value here as 1/2. And suddenly, that makes it so much more friendlier in order to face this exercise here. Because now, instead of having a cosine pi divided by 3 and a bunch of weird stuff, you just have a 1 divided by 2 multiplying everything. Now, how the heck did I just do that, right? I mean, that's the whole point. Let's learn what's happening. So, we usually talk about SOHCAHTOA, right? And SOHCAHTOA, ladies and gentlemen, is a way to be more familiar with sine, right? With cosine and with tangent. And so is for opposite over hypotenuse. Ka is for adjacent over hypotenuse. And toa is for opposite over adjacent. Now, if we're talking about the unit circle and we're talking about some line that goes like this at an angle of pi divided by 3, right, or the same as 60 degrees, see? And you know that this last point, okay, is 1/2 comma square root 3 divided by 2. Well, notice, we are talking about the unit circle. Unit circle. Unit. One unit. And so, this point here is 0, 1. This point here is 1, 0. This point here is 0, -1. Sorry, I almost trolled. And this point there is -1, 0. Okay? Why is this relevant? Well, if you have those 4 sort of corners in your XY graph for the unit circle, well, that's basically telling you that the radius, and I know this is not joint or scale, but the radius has to equal 1. And so if the radius equals 1, that means that you also have a radius of 1 right there. Actually, all along your unit circle, connecting to any one of these points, you have a bunch of radiuses equal to 1. And this is very important to understand because that means that this triangle that I'm putting now, well, what do you know about it? So that triangle right there, okay, because this is pi divided by 3, okay, and you know that all of the radiuses are equal to 1, and you know that this point, see, is 1/2, comma square root of 3 divided by 2, well, the 1/2, right, is your x value, see, and the y is square root of 3 divided by 2. And so you know that the dimensions of this triangle have a height of square root of 3 divided by 2 and the base or whatever of 1/2. So cosine was adjacent over hypotenuse. And so all along your unit circle, all the hypotenuse are equal to 1 because your radius equals 1. And what is the adjacent in this case? Well, the adjacent, right, of this angle is the one right next to it is simply 1/2. Okay, so the hypotenuse is always the long side. It's always the one opposite of the 90 degrees. It's always the radius. And so now you can actually apply that because you have cosine of pi divided by 3, you remember the dimensions of this triangle by memorizing this coordinate, right? And through there, you can pretty much establish that, okay, so cosine of pi divided by 3 is quite simply the adjacent, 1/2, divided by the hypotenuse, which is 1. So that's just going to give you 1/2. So that is why I ended up plugging in, okay, by doing adjacent over hypotenuse, that cosine pi divided by 3 is simply going to be 1/2. The other way you can think about it is that, okay, so because the hypotenuse equals 1 in this case, the adjacent has to be the x value. And so what's the x value of that coordinate? 1/2. The same thing works. If we were talking about opposite, yeah, then it would have been the y value, okay? Anyways, enough blah blah. That was just a quick but super essential explanation of how cosine pi divided by 3 ended up being 1/2. So it fully has to do with being familiar with the unit circle and understanding all the triangles that come out of it. Remember, the radius equals 1. That will make your life so much easier. So remember, sine, cosine, tangent, so, ka, toa. It's going to save you. See? Anyways, back to reality. Here we can now start solving for t. And so yes, this looks nasty. Yes, it looks hard to solve. But notice you only have one variable, which is t. And you're actually pretty close to showing that this is true, right, for part A. And so notice, we have something very similar, but we're not quite there yet. And so the first thing we can sort of try to establish is that, you have a 4t on the left, so we should probably try to do that first and then see what happens on the right. See? So if we go ahead and do that, we would have to multiply 2 to both sides. This goes away with this. You do end up with 4t equals square root 2 times square root of 5t squared plus 6t plus 9. Now, how do we go from there to what we have over here? Well, it's a fairly, I mean, not simple, but it's just how square roots behave. See? So in this context, because you have square root 2 times this whole other thing, and the square roots are multiplying, this is very important because the square roots are multiplying, this is the same as rewriting it as quite simply the square root of 2 times the whole other thing. Okay, you can sort of like merge the two square roots together, but do it appropriately so that the 2 multiplies everything, okay? That means that 4t has to equal square root of 2 times the 5t, so 10t squared, 10t squared, plus 2 times the 60, so 12t, plus 2 times the 9, which is 18. And now, ladies and gentlemen, we have something awfully similar, if not the same, to part A. 4t equals square root of blah, blah, blah. 4t equals square root of blah, blah, blah. Checks out to me. So that is how you solve part A, and I think the hardest part really has to do with understanding how the formulas work and how to get rid of the cosine pi divided by 3. right? So I hope you learned a thing or two. That is for part A. For part B, all you really need to I'm getting a lot of voice cracks today. It's caught my attention lately. I'm not sure why. Oh well, who knows? Okay, now for part B, you need to find the value of t. Okay, so for finding the value of t, well, this equation, although it looks very, very nasty, there's one thing going good for us. The only variable you have going around is the variable t. And so because the only variable you have going around is the variable t, all you need to do from here is get t alone. Now, the most annoying thing to deal with right now, at least, okay, is the fact that you have a square root in there. And so how do you get rid of a square root? Well, in order to solve the square root, the best thing I can suggest is squaring the square root. Now, the reason you would do this is because much how like multiplying is the opposite of dividing, well, the opposite of square root is squaring whatever you have, okay? So 4t equals this whole thing. What you can do, just give me a moment because I do need to make a little bit of space. So what you can do from here in order to get rid of the square root, because it is the most annoying thing, is just literally square both sides. Okay, instead of like dividing by 2 or whatever, you can also square both sides. This is completely legal. So 4 squared gives you 16 times t, t squared equals, this goes away with this. Look at that, how beautiful, see? So from here, well, you want to get everything to one side. So I'm just going to go ahead and do minus 10t squared, right? And really, I'm going to minus everything else as well. So minus 12t minus 18. So after you do all those steps, you end up with 6t squared minus 12t minus 18 equals 0. So all I really did is was throw everything over to the left. Now from here, you do want to solve for t, correct? Now, solving for t from here, you should be establishing like a bunch of different rules in your head because you should be recognizing this by now. You are dealing with a quadratic. Okay, and when you're facing a quadratic, there are a bunch of tools that can come to mind. Actually, even in your formula booklet, in the part of quadratics for functions, okay, you do have this right here. So solutions of a quadratic equation, which is literally what we're doing right now. The formula you can follow is this guy right there. Okay, so if you follow this guy, you will be solving this much more easily. See, now one approach you can do, right? I mean, following this equation here is just immediately establishing like, ah, yeah, so A has to equal 6, B has to equal negative 12, and C has to equal negative 18. And from there, you can plug into the formula that they ask you to use, negative B plus or minus square root B squared minus 4AC divided by 2A. This will help you solve for T, okay? But we're in HL, okay? We know a thing or two to make our lives easier. From here, you could have established or noticed that on the one hand, all of these are even, so you can divide them all by 2. But you can notice even faster, you can divide all of them by 6. So if you divide all of them by 6 on both sides to make it legal, on the right side you have 0 divided by 6, nothing really changes. On the left side you end up with t squared minus 2t minus 3 equals 0. And so now it's suddenly a lot easier to like solve, and you can again establish that a equals 1 because you have a 1 times t squared, correct? B equals negative 2 and c equals negative 3. And so from here you can now apply the quadratic formula, and it's going to be much faster or easier to solve, and you can also factor from here. Okay, so let me just I got time, I'm going to show both. You can skip ahead if you want, but using the quadratic formula it would look like this. So x equals negative b, so it's negative negative 2 plus or minus square root of negative b squared minus 4 times a, which is 1, times c, which is negative 3, divided by 2, parentheses 1, right? So solving all of this piece by piece, well, the negative times negative is positive 2 plus or minus square root of 4, and this is negative times negative, so it ends up being plus 12 divided by 2. So from here, x equals 2 plus or minus square root 16 divided by 2. Square root 16 is just going to be 4. So the two paths, it's literally two paths, the two paths you gotta take is the path of positive or the path, whoops, of negative. Your mentality is a decision every day. So x equals 2 plus 4 divided by 2, or x equals 2 minus 4 divided by 2. So up here you end up with 6 divided by 2, or 3, so x equals 3. And on the bottom, okay, you end up with x equals negative 2 divided by 2, so x equals negative 1. So basically what you're establishing is that t, right, because I know we plugged in x here, but in this context, really what you're saying is that t equals 3 or t equals negative 1. So t equals 3 or t equals negative 1. Now, just going to check here quick. Yes, t equals 3. Beautiful. Um, which of these is it? Because this is for or, right? Like it's one or the other. So which one should it be given this context? Remember how I said that anything that AB gives you is super relevant? They did tell us 4,397 years ago that t is greater than 0. And so in this situation right now, you would choose t equals 3 instead of t equals negative 1. All right? So that is solving with the quadratic formula. See, if you want to solve it by factoring, you can do that too. I'm just showing all the tools that you can establish here. Now I know that I'm a little bit of a boomer, so I do factor in a different way. But you millennials or whoever's watching, right, maybe the Zoomers, who knows, I have no idea, have a quicker way of doing this. So the way that I do for factoring is that I do this times this. Okay, so the 1 times the negative 3. So I have to think of the factors of 3. Really, I only have 1 and 3, right? And now I need to establish, okay, in which way, because they're the only factors, ¿cierto? Can I multiply them together to give me negative 3, okay? Multiply them together to give me negative 3, and add them in order to get negative 2, see? And so clearly you end up establishing that you need to multiply by negative 3 and positive 1, see? Because that means that you can do t squared. I mean, really, just skipping a little bit, you end up with you end up with t plus 1 times t minus 3 equals 0. And from here, because you have two parentheses equaling 0, that means that either this one is 0 or either this one is 0. See, because it is two numbers multiplying each other giving 0, one of them has to be 0. So t minus 3 equals 0 or t plus 1 equals 0. So from here, t equals 3 or t equals negative 1. And once again, because t has to be greater than 0, we pick that t has to equal 3. See? So a little bit of a longer explanation on what to do with the quadratic part. If you don't realize these tips and tricks and you solve it from here like that, it's going to work. Okay, don't worry. If you follow the procedure, it will work. Trust me. Okay, I think even the mark scheme does it like that. See, the mark scheme uses the big value numbers and you're still going to end up with the same answer. Okay, so keep it in mind. This is just a way to make it a little bit more friendly. If you realize you can divide by 6, but you don't have to. Okay, follow the procedure. It might be a little bit longer, but it's still going to work. That is what we're looking for at the end of the day. Procedures that work, formulas that are reliable. So that's the one I shared with you today. And yeah, that is for part B. All right, you guys, and now for part C, they tell us with these very important words, hence or otherwise. So basically, using from before, hence or otherwise, find the shortest distance from A to L1. So, because it says hence or otherwise, it is key information that what we found in part A and part B is going to be 100% relevant for part C. So this is a big, big hint that, dude, whatever you used before is essential. It is very, very important. So we did find out earlier that t equals 3. Okay, and we're going to find the shortest distance from point A to L1. And so here we need to apply a little bit of logic. See? So let's think about the shortest distance from point A to L1. And so on the one hand, you have this distance that goes like this, right? But then you might be thinking, if you move the angle just a little bit, you can get there much faster, right? The black line is definitely shorter than like the purple one, right? But now when we start putting the green line, right, that's even shorter, isn't it? And eventually you're going to realize that the shortest distance is actually one that is perpendicular. If you keep moving like this visually, you will realize that the perpendicular one is the shortest distance. And this is a math rule that, for me at least, it's very visually appealing. But if you do want to memorize it or learn it in the more hardcore way, you would say that the shortest distance from a point to a line will be like when it's perpendicular. Will be when it's perpendicular. Okay, so whenever it's perpendicular, that will be the shortest distance. Okay, and so this triangle that I just drew in pink that goes like this, boom, boom, boom. Well, what do you know about it? We did establish like a million years ago that the acute angle between the two lines is pi divided by 3. So that means that right here you have a pi divided by 3. Now, what else do you know about this triangle? Well, on the one hand, the shortest distance, right? The shortest distance, which I'm now putting in, let's say, red. So the shortest distance, which I will call x, is this x right here. So we need to find that distance, okay? So we need to find that x for the answer in part C. Now, they did tell us that hence or otherwise, we need to find the answer, and so we need to use t equals 3. Now, t equals 3, where does that even go into our equations, right? T shows up there and there. So, okay. So for now, let's just go ahead and plug in. So if you plug in t equals 3 here, you're going to end up with 2 times 3, 0, and 3 plus 3. So you're actually going to end up with PA, right, is going to be 606. Now, why is this useful? Okay, well, PA, and because it has this little line, correct? So because it has the little line, it's basically like the direction vector of PA. It's like some weird sort of like concept going around. It's like the direction vector. See, so it's basically like if you put a vector, then its direction vector, it's 606 like that. Now that isn't exactly distance yet. And so how the heck do you find the distance of a distance vector? I mean, like, what's going on there, right? And so the next key sort of concept that I need to share with you is that the magnitude of a vector equals its distance. The magnitude of a vector will give you its distance. And that right there is huge. So basically, if you find the magnitude of this guy here, you're going to be finding the distance that goes right over there, which is along the hypotenuse. And so you can start really filling in the dimensions of the pink triangle and solve this exercise more thoroughly. So, of course, we need to go to the trusty rusty formula booklet because it will save your life. So, might as well learn it, might as well know what's in it. For this part, we need to go to topic 3, geometry and trigonometry, HL only because we are now part of the Cool Kid Club. And boom, here is magnitude of a vector. So this is like the thought process you have to go for. See? You drew the pink triangle. You realized you needed a couple more dimensions in order to figure out what x is. And you said, we just had that t equals 3. So you plug it in where you can, and you find that the direction vector of PA gives you 606. Now that's not a distance, so it doesn't help your pink triangle yet, but you can figure out the distance because this guy online told you that the magnitude of a vector equals its distance. And so you remember the key word, magnitude. You know that's in your formula booklet. You go and open it. You go ahead and find it. Here it is. So let's go ahead and plug that in. Basically, the magnitude of a vector, right? For magnitude, we put in an absolute value. So magnitude of vector is going to be the square root of the first one. That's why it's v1, right? The first one squared plus the second one squared plus the third one squared. Which one is the first, second, third? Well, it follows this order here. So from top to bottom, that's the first, that's the second, and that's the third. And so following that sort of logic, the magnitude of PA, right, which is basically just going to be this distance, correct, is going to be square root of the first one, which is 6, so 6 squared, plus the second one squared, which is 0, plus the third one, which is 6 squared. Okay? So if anyone's still a little bit lost, this is your V1, this is your V2, this is your V3. Okay? So we go ahead and plug in. What you end up with is that the magnitude of this guy is going to be, well, 36 plus 36, so square root of 72. And so this distance right here that we just discovered is actually square root of 72. And so now using this triangle, suddenly it's a lot more friendly what you have to do. So now it comes down to trigonometry. Why do we use trigonometry? Because you are dealing with trigonometry triangles. So because you have a 90 degrees here, it's very useful to consider the tools that trigonometry brings. So trigonometry, the main thing we can do from here, you guys, is what we call the SOHCAHTOA. See? So you have sine, cosine, and tangent. And so let's remember that each of these can be remembered as SOHCAHTOA. Now, why do we remember it as SOHCAHTOA? Because SO is opposite over hypotenuse, while ka is adjacent over hypotenuse, while toa is opposite over adjacent. So in this case, oh, and this is all in respects to your angle. So the angle that you have is this guy right here. And so you have the hypotenuse, all right? So we will be using so or ka for sure. So we can immediately discard toa because, well, we have to use the hypotenuse, right? And next we say, okay, we need to find x, right? Now x, is it adjacent or opposite? It is opposite to your angle, see? So because it is opposite to our angle, we will be using sine or so, see? So if you go ahead and plug in a sine, in this case, you will be doing sine of your angle. So sine pi divided by 3 equals opposite over hypotenuse. So my opposite is going to be x. My hypotenuse is going to be square root of 72, right? And now from here, it gets even juicier because we did mention a while ago that the unit circle, okay, can help you find what pi divided by 3 is as an angle. See, so this is in radians, okay? So that means that if I go ahead and open up the unit circle, which is actually something that you need to memorize because you are an HL and you do have to memorize this kind of stuff or learn it in your own way, you can see that the 30 degrees, or sorry, the pi divided by 3 is right here on 60 degrees, right? So let me just go ahead and draw that real quick because it is very relevant. So in my unit circle, right, you have here the point 1 comma 0, you have here the point 0 comma 1, you have here the point negative 1 comma 0, and you have here the point 0 comma negative 1. So we just established that pi divided by 3 as an angle is right here. So there we have pi divided by 3. And what point is it at? It's at the point 1 half. So this right here is 1 half, comma, square root 3 divided by 2. Now we need to understand the following. So this dimensions here, right, this point, the 1 half comma 3 divided by 2, is basically telling you that, okay, this is my x. So that means that over here, you have 1 half. And for your y, over here, you have square root 3 divided by 2. That's what it's telling you. So at sine pi 3 divided by, at sine of pi divided by 3 in radians, right? So sine of pi divided by 3, you have those dimensions there. Now, sine, as we mentioned, is for so, and so is opposite over hypotenuse. But ladies and gentlemen, in my unit circle, right, in my unit circle, all of my hypotenuses are equal to 1. Because the unit circle, notice, it has a bunch of 1, 0 here. 0, 1, negative 1, 0, 0, negative 1. So that means that all these different radiuses are actually just 1. See? And that includes this one here. Basically, what I'm trying to tell you is that if you have sine of pi divided by 3, and you memorize or remember that these are your x and y values at that point, okay, you can apply so. And the opposite in respects to this angle, you will see that it's this guy here. Okay, so the opposite of your angle in SOHCAHTOA, and with SAW in this case, is the square root 3 divided by 2. The other way you can sort of like memorize it is that if you're talking about sine, then this will be giving you the y value. Okay, so the y value at that point is this guy here. So in other words, the SAW in this case will be the opposite, so square root 3 divided by 2, divided by the hypotenuse, which is just 1. So this equals square root 3 divided by 2 divided by 1, which is just going to give you square root 3 divided by 2. So all of that was just to leave clear that sine pi divided by 3 here on the left is going to give you square root 3 divided by 2 because it's the y value in your unit circle for sine pi divided by 3. Okay? That is the sort of concept jump that I was trying to make. So square root 3 divided by 2 equals x divided by square root 72. Now you want to get x alone because you want to find the shortest distance from A to L1, which we did call x. So from here, what you can do, because you have two fractions on both sides, you can cross multiply. I mean, really, you just need to get x alone, and the most common way is that you do this times this and this times this. So 2 times x equals square root 3 times square root 72. Now, from here, two interesting things happen. Because the square roots are multiplying each other, what this actually ends up being is they sort of like meld. So it's 3 times 72 inside. Okay, so 2x equals whatever that is times 3. So it should be 140, 210, 216. So square root of 216. That's interesting. So x equals square root of 216 divided by 2. Now we should probably try to simplify this as much as we can. And looking at the mark scheme, let's see how far we have to go. Well, you don't have to go that far actually. You can just leave it like this. So leaving it as square root 216 divided by 2 is good enough. If you want to simplify it more, it seems like you can. For our interests, we will just leave it like that. Okay? So there's my value for x, and that would be for part C. Alright, you guys, and now for part D, okay, they tell us that a plane, right, with this symbol, contains L1 and L2, and we need to find a normal vector to that plane. Now, what the heck is a normal vector? What is going on, etc. So, the word normal in this context is not very normal. It's actually quite confusing, to say so myself. So, on the one hand, imagine you have like a sort of quadratic, okay? Imagine you have like a normal sort of quadratic that goes a little bit like this, okay? And let's say that they tell you that there is a tangent, okay, at x equals negative 1. Sorry, at x equals, yeah, at x equals 1. So at x equals 1, right? Right here they tell you, here there is a tangent, okay? So that means that at that tangent, and this is the main idea of tangents really, okay? At that tangent, the slope is the same as the quadratic. So at x equals 1, you have a line that goes something like that. It touches once and never again because it has the same slope. Okay, so there is my line that wasn't drawn perfectly, but point is, this is a tangent, okay, that has its slope equals the quadratic, okay? The slope equals the quadratic at that point, okay, because the slope of the quadratic does change over time, but at x equals 1, they have literally the same slopes, right? Now, Similar to the idea of a tangent, you also have the normal. And so the normal is actually going, how it looks like, let's go over that first. So how it looks like is that at the same point, it's actually going to go like that. Boom. So what the heck is happening here? So here, at the same point, the slope is actually going to be perpendicular to the quadratic. Okay? So when it is normal to the curve, you have a slope that is perpendicular. See? So you can actually literally just sort of say that it's like, well, it's pretty much just the inverse reciprocate, right? Point is, when you have something normal to the curve, it looks like this. It will be the perpendicular to the original sort of slope. Okay, the inverse, however you want to think about it, etc. So in this case, a normal vector has a fairly similar idea. It's basically a vector. Okay, if you have a normal vector to the whole plane, then that means that for both L1 and L2, it sort of cuts them like in the same way that it cuts this quadratic here, right? So normal to them, the slope is sort of like the inverse and stuff like that. Now, because we're talking about vectors, the approach is very different, but I did want to share the idea that that is what it means by normal. Okay, so that means it penetrates them in a certain way. Visually would be something a little bit like this. Now, because this is 2D, it's easier to explain, but if we were talking about a vector, we're talking about 3D plane. That is why it has 3 coordinates there, so it's a little bit more different, okay? But regardless of that, I just want to share the idea of what it means by normal, okay? Now, how do you actually find a normal vector to a whole entire plane? The procedure is awfully specific, and it is actually so specific that there's only one method. So I'm just going to show you in the mark scheme. There's literally like only one way to solve it. It's right here, right? So this is a sort of specific thing that I unfortunately do have to tell you. This is the kind of thing that you just have to know, okay? So the kind of thing that you just have to know is that, well, basically, for finding a normal vector to a plane, you need to find the, let me use the same words, the vector product, okay? The vector product of two direction vectors. So, the vector product of two direction vectors. Now, direction vectors, you guys, is basically taking a line and being able to define the direction that it's taking. Okay, so it's sort of like the slope of these 3D figures. You can think about it that way, okay? And so really, the direction vector can be like from here to here, or it can also be from here to here, or it can also be from here to here, because really, they're all going in the same direction, right? And so why do I establish that? Because the moment that they give you the direction vector of PA, well, PA, they did tell us, right? PA lies on L2. And so the direction vector of PA is the same as the direction vector of L2. Okay, this, you can replace it and it's going to be the same thing, right? So the direction vector of PA also gives you the direction vector of L2. It's the same idea. So what the heck is PA in this case? Well, let's recall that we plugged in t equals 3 earlier. That will give you 2 times 3, 0, 3 plus 3. So really the direction vector of PA, which is the same as L2, is 6, 0, 6. Okay? Now, that being said, right, for the normal vector, we did say we need to find the vector product of two direction vectors. So here are my two direction vectors. One is right there, and my other one is right here. So how the heck do you find the vector product of these two guys? Well, that is the next big buzzword that you need to identify. Vector product in your formal booklet is right there. So getting familiar with the formal booklet is absolutely essential. Now, looking at this format over here, well, it's obviously a little bit harder to follow. So actually, I think it might be wiser if we bring the process over here. So my first direction vector, right, the v, which we call L1, equals, so direction vector of L1 is 1, 1, 0. And the direction vector of L2 is this guy here, right? it's going to be 6, 0, 6, right? And now if you go ahead and plug into the formula that is right there for the vector product, following the procedure that they tell us, for example, the one on the top left, you guys, is V2 times W3, which is basically the second one of the first times the third one of the second, okay? So just be very careful in your approach and it's all going to work out. So the first term of your vector product on the top left is going to be V2, so it should be 1, so this guy 1, times the last one of the second, so 1 times 6, minus, okay, V3, which is going to be the last one of the first, times the second one of the second, see? It's going to be, so 0, correct? So 0 times 0, actually, look at that, yeah? And basically, you just keep going from here and you're going to solve it, see? So V3 is going to be 0, so 0 times W1, which is 6, minus V1, which is 1, times the last one of the second, W3, times 6, right? And then this last one over here, you have V1 times W2, so that's going to be 1 times W2 is 0, minus V2, which is 1, times W1, which is 6, see? So you go ahead, you do all that math, you're going to end up with 1 times 6 gives 6, minus 0 is 0, okay? 0 times 6 is 0, minus 1 times 6 is negative 6. And down here you have 1 times 0 is 0, minus 1 times 6, which is just going to be negative 6, see? So basically it's 6 and then negative 6, negative 6. So this is the vector product, okay? This is the vector product. Now I did mention earlier that, for finding the normal vector to a plane, you need to find the vector product of two direction vectors. So really, the vector product ends up being the normal vector. So vector product will end up being your normal vector. So your final answer is actually going to end up being like 6. For over here, the normal vector is going to be 6, negative 6, negative 6. See? Now, there is one observation I have to do here, okay? And that is that for the direction vectors, all you really care about is like the magnitude, see? Because in this case, they did tell us that the direction vector of PA, so from here to here, was 6, 0, 6, right? But if I, for example, found the direction vector of, I don't know, from P to some point that I'm going to make up, like B all the way up there, right? So all the way up there, see? Well, the direction vector of that would probably end up being something like 12, 0, 12. Now, what is the observation that I'm doing here? These direction vectors are the same, technically, because in proportion, they're the same, see? For example, this one, you can divide both of them by 6, you end up with 1, 0, 1. This one, you can divide both of them by 12, you end up with 1, 0, 1 as well. And so basically, the proportion of your direction is what you care about the most. In other words, it doesn't really matter if you take like the slope. I know it's not literally the slope, but let's understand it as the slope. It doesn't matter if you take the slope from here to here, or from here to here, or from here to here. They're all going to be the same slope. And so, to leave like your final answer down here, technically you can divide everything by 6. And you can end up with a nicer normal vector, which is 1, negative 1, and negative 1. Notice that the mark scheme does something very, very similar. You end up with 1, negative 1, negative 1. But it does tell you that any scalar multiple of this also gives you the point. So don't worry if you didn't notice that, okay? What I'm trying to tell you is that you can leave it like this or you can leave it like that. Both of them work. I just need to share the idea that what you really care about is the proportion of your direction vector, of your normal vector, okay? That's what vectors are really all about. It's about the proportion that they share, okay? If you're talking about magnitude or distance, then that's a different story. But if we're talking about direction vectors and stuff like that, you really only care about the proportion, that they share. So, ladies and gentlemen, that is how you do part D. All right, you guys, and now for this last one, okay, for part E, we need to do a crazy exercise that is worth 7 points. Now, the math is not that complicated, but the concepts behind it are really, really wild. Okay, so better make sure you lock in because we're going to be cooking on this one, all right? So, for this last one, we have that the base of a right cone lies in basically our plane. See, so let's remember that that symbol there is for the plane that we're dealing with, and it is centered at A, so that is, quite useful. It is centered at A such that L1 is tangent to its base. They also inform us that the volume of the cone is that amount of cubic units. And so we need to find the two possible positions of the vertex of the cone. All right, so clearly there's a lot of different buzzwords going around here, and so we really need to try to identify basically what the heck is going on. Okay, so first things first, visually on this diagram, we already identified that triangle there. We know that that small sort of like height, like the x value that I'm putting is square root of 216 divided by 2. We did that from earlier, right? And so what's happening now is that at point A, right, it is centered at A, we are drawing the base of a right cone. So let's remember that a cone looks a little bit like this. Boom. Okay? There is your right cone. All right? And so the right cone, actually, let me make it like a little bit of a better drawing. So the right cone looks something like that. Okay? So here is your right cone, right? And so if I'm drawing just the base of the right cone, it's just going to be a circle. And so because the base of the right cone is centered at A and is tangent, okay, with the L1 basically, because it's tangent with L1, that means that your circle for your right cone goes something like this. Okay, let me make it a little more centered, but it will look something a little bit like that. Okay, so basically there is the base of my cone, see? And right there, it's going to be perfectly tangent. Now that is extremely useful because since it is perfectly tangent, then this red line right there, you guys, is actually my radius. Because A is the middle of my circle, and because here it is tangent, that means that from A all the way until we hit L1, it has to be the radius of the base of my right cone of my circle. So that is the first big observation that we really need to do. Now, the second thing that we need to establish is that it is asking for us to find the two possible positions of the vertex of the cone. Now, why the heck are there two possible positions? Well, because technically this cone can either go out sort of like, I'll try to draw it, okay? So it can either go out this way, and the height is like this, okay? And basically I want you to find this location here, all right? So that would be one of my vertexes that it can take, or it actually goes out this way. Boom. And that means that my vertex would be over here. Now, the one sort of friendly thing about this exercise, if anything, is that these two heights are the same. And so it's the same height, but the vertex would end up being different. Okay? So keep that in mind. All right? Now, before I jump into like what to do and how to do it and etc., okay, we really need to establish like our way of thinking. Okay? So on the one hand, they did give us, okay, they did give us the volume of the cone. So they tell us that the volume of the cone is this amount. See? And so let's just sort of play around and see what that might give us. Okay, whatever the IB gives you something, you probably end up using it. So I'm going to go up here and say that volume cone, they tell us that it's 90 pi times square root 3. However, what is the formula for volume of a cone? I mean, if they're giving me the volume of the cone, well, what's the formula for it? Now, you probably don't know it by memory, and surprise, neither do I. You're not supposed to because you have the formula booklet. So open up the formula booklet. Let's go ahead and find volume of a right cone. So here's the volume of a right cone. See? R is going to be the radius, pretty standard. H is going to be the height. So volume of a cone with big V, okay, to show that it's like the formula, okay. So volume of a cone is a third pi r squared times h. So if they give me the volume of the cone right there from the exercise, and I have the formula from the formula booklet, well, you can equal them to each other, see? So technically, I should have that 90 pi times square root 3 equals a third pi r squared times h. Now, I'm not exactly excited about this yet because I do have the two variables r and h. So, do you have either of these? Surprise! Yes, you do. You have it right here from the radius, which we said earlier was square root 216 divided by 2. So, you can go ahead and plug that in and end up with only one variable. So that is just fine and dandy, as some people say. So, 90 pi times square root 3 equals a third pi times my radius, which you said was square root 216 divided by 2, and all of that squared times h. And so now you only have one variable, only h. Okay? I don't know why I put an r initially. But you have only h, see? And so now you can actually, well, work this out, and although it looks terrible and it looks scary and it looks horrifying and there's square roots and squared and pi and doom, you do have only h. So you can actually find like an h equals something, see? I mentioned this because lots of times in my videos, or just in math in general, I think it's very easy to get lost in the sauce. It's very easy to like lose grasp of like, okay, why am I doing what I'm doing? Okay, and so in this case, they gave us the volume of the cone. We applied the formula for volume of the cone, and we said, okay, this is gonna give me something. See, so you plugged it in. You realized you had two variables, r and h. You slowly realized, I have r, so let's plug in r, and now you have only h. So this will give you h, which means that in this diagram you will have this value here, which is actually the same value as this value here. Okay, so that is the h that we're finding right now. And so basically I can just start from A, apply H, and we're going to see how that works. Okay, so we're going to start from that point, apply H, and that way we find the two vertexes, okay? Or vertice or whatever. Is that it? So how the heck do you get H from here? Well, just get H alone, see? So H is on the right side, do everything to throw all this stuff over to the left side, see? Now let's make it as friendly as possible. So basically what I would start off with, okay, is that, well, the left side, I'm just going to leave it the same, to be honest. On the right side, I end up with 1/3 pi, and I'm going to apply the parentheses. See, I mean the squared on the parentheses. So, because it's squared, you end up with square root 216 times square root 216 divided by 2 times 2. Okay, so that means you end up with 90 pi square root 3, and technically this 3 I can just pass it over immediately, so you multiply by 3 to both sides. That means over here I would end up with 90 times 3, so it's 270. Alright, so that way I got rid of the 3 right there. Pi, parentheses, 216, because square root and square root just gives you what's inside, divided by 4, okay, times h. From here, because you have pi on both sides, that means you can divide by pi on both sides, just get rid of it. So on the left you have 270 square root 3 equals whatever this is. See? Now this, after a long time of thinking and figuring it out, you will discover that it's 54. So 270 square root 3 equals 54h. Divide by 54 to both sides in order to get h alone. H equals 270 divided by 54 is going to give you, let me do some big brain maths, 5. Okay, so you end up with h equals 5 square root 3. Okay, so boom, look at that. You just found that h equals 5 square root 3. Now, what the heck do you do from here? Okay, so as I mentioned, you want to start from this origin and sort of like apply h. Okay, I'm just saying it more intuitively. Start from the origin, which is a actually. Start from the origin, which is a. The letter a is right there, see? Start from the origin, which is a, apply h, and end up, okay, at one of the vertices, see? Now, when you sort of like apply h, okay, you really need to understand that you are moving along some sort of line, some sort of vector that is going this way or this way, see? Now the big issue here is that do you have a vector that actually does that? All right. And this is where I really need to try to draw some masterful art because explaining this is actually really tough. Yeah. So this is what's happening. Right now you have an XY plane. Okay, that goes like this. Okay, I'm doing it like as 3D as possible. See? So you have some XY plane that goes like that. Okay? Boom, boom, boom. It goes something like this. Okay, and this whole thing, okay, is plane whatever that symbol is. Okay, so this is plane like big pi, I don't know, whatever. Okay, so this is what's happening. In this exercise, we drew, okay, the base of the right cone. Okay, and basically we need to find one of the vertices that goes like that and the other one that goes like this. See? Now, in order to really do that, you need to be able to move along the plane, okay, in a perpendicular way. Because since it is a right cone, and this is another big idea I need to share, see? Because it's a right cone, that means you have 90 degrees here, and the cone going sort of like all around it. See? Now, notice, this basically, okay, maybe now it's going to be a little more clear. This down here, okay, this is your plane. This is the plane that you're trying to like draw or figure out, see? And so this right here on your circle down below is your plane, and you need to find some vector, okay, that will allow you to travel through here and also through there in order to find the other vertex, okay? That's what's happening. And so which vector allows you to do that? The normal vector. Let's remember that I mentioned a million years ago that the normal vector, exactly what it does, is that it gives you a line or a vector that's perpendicular to your plane. And so a line that is perpendicular to your plane actually helps you find that height, all right? That height for your right cone, okay? And that will actually allow you basically to travel through here and allow you to find the two vertices, see? So if I return to this drawing over here, basically your normal vector, so your normal vector, what it's really going to do is that it's going to be perfectly perpendicular to this. So it's going to call like that. Boom. There's your normal vector. And all you have to do now is travel h amount of units, basically, in order to find one of the vertexes, and h amount of units over here in order to find the other vertex. Okay? So there was a little bit of blah blah for understanding why we're doing what we're doing. Essentially really has to do with understanding the normal vector. See? So it's no surprise that for part D, we did have to find that. Okay? Now, the normal vector we found from part D has these sort of like properties or whatever. See? So the normal vector has that, you know, those coordinates, if you want to think about it that way. Okay? And so essentially what we're establishing now is like, okay, so you gotta basically take your normal vector, okay, in terms of magnitude, because for distance, see, so take the distance of your normal vector and apply it enough times so that you reach h, okay? Now apply it enough times, right? Apply it enough times. So some amount times your normal vector until you reach h, okay? Basically, if I were to like redraw it again, because I think it's very, very important that we understand this part, okay? Basically, you have some normal vector that I'm now going to put, say, like in pink, that goes like this, okay? And all you know is that you need to multiply this some amount of times, maybe 2 times, maybe 3 times, maybe 4 times, until you fulfill and reach the distance of h, okay? And so that is why you got to take your normal vector, multiply by some amount, which we will discover now, and get h, okay? So if you go ahead and start filling in what I put on the left just now, you're going to discover a couple of things. So on the one hand, okay, well, that's some amount, which I'm putting as u. We still don't know yet, so you can just leave it as u. Magnitude of n, when we talk about magnitude, we're really talking about distance, and we do come back to Where is this fancy formula? Ta-ta-ta. Wow, I am blind as a bat today. There it is, magnitude of a vector. See, so you go ahead and plug in this formula here. See, now we did use it for like part B, I think it was, or C, I'm not sure. So I'm not gonna go over it very thoroughly, but basically this first term is the one up top. This second term is the one on the second. This last term is the one on the bottom. See, so for the magnitude of a vector, you're just adding all of them inside of a square root, and they are all squared. So in this case, for a magnitude of n, see, knowing that n is 1, -1, and -1, ¿cierto? From here, nice. That means that magnitude of n is going to be square root of 1 squared plus -1 squared plus -1 squared. And so you're quickly going to realize that really this is just 1 plus 1 plus 1. So magnitude of n equals square root 3. So you can plug in that magnitude of n equals square root 3 right here. And h, we found from earlier, is 5 square root 3. And now it's really no surprise that you, okay, I mean really the last step you want to go hardcore is that you divide by square root 3, divide by square root 3, boom, 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 boom. U has to equal 5. Now, here's a very important thing that we need to establish. So because u equals 5, well, the vertex can either go up, like this diagram that I put here, or the vertex can be down here, right? And so u, ladies and gentlemen, basically how many times you apply the normal vector, can either go up or it can go down. It can go left or it can go right. So u has to be plus or minus 5. All right, awesome. So now that we mentioned this, for finding the position, the two different positions of the vertex, okay? Well, first, what the heck is point A? See? So you are starting at point A. It is the origin of your right cone. See? Now, point A, something we didn't establish earlier, is that it's actually 2t, 8, and 3. And from part B, you found that t equals 3. So point A is actually 2 times 3, 8 comma 3. So point A is 6, 8, and 3. ¿Vale? Now, so you're starting from 6, 8 comma 3. You're applying, we discovered, the normal vector 5 times either positively or negatively. So let's literally like put that in writing. See? Enough blah blah. Let's get into it. So vertex 1 basically is going to be your point A, which is 6, 8, and 3, plus 5 times, okay, n, or you're going to have 6, 8, 3, minus 5 times n. See? N as a vector, ¿cierto? So the vertex 2 is this one down here, and the vertex 1 is that one up there. See? So let's go ahead and do vertex 1 for now. So n, as we've already established a couple of times, I'm just erasing it to make a little bit of space. So n is 1, -1, -1. See? So vertex 1 is really just going to be 6, 8, 3 plus 5 times 1, -1, -1. See? Which really, I mean, if I'll leave it like in some fancy sort of vertex form, you can do it like this, okay? Actually, I think it's more intuitive, sorry, if I leave it as coordinates, okay? So 6, 8, 3 plus 5 times 1, -1, -1. See? So in this case, you end up with 6, 8, 3 plus 5 times 1 gives you 5. 5 times -1 gives -5. 5 times -1 gives -5. So from here, okay, really, if you want to do like the more rigorous sort of step, okay, you would end up with 6 plus 5, which is basically this one plus this one, okay, and then 8 minus 5, which is this one with this one, okay, Let me just finish color coding, why not? And then the last one would be this one minus this one, okay? Which is going to be 3 minus 5. And so this last point ends up being 11, 3, and -2. So this will be your vertex 1, okay? So now probably the procedure makes a lot more sense. I think the hardest thing that I needed to explain was why the heck we used the normal vector in the first place. And really, visually, it's a hell of a challenge. See? So find your own way to understand it, whatever floats your boat. That it? So that is for vertex 1. And for vertex 2, you follow an extremely similar procedure, just that instead of plus, you will be doing minus. See? So really, I can just do it from here. So instead of plus, we're now going to change it to minus. So that means that over here, I end up with -5 plus 5, okay? And I mean positive 5, see? So that means that when I combine everything, okay, I mean really this point ends up like this. Okay, this is like the big change that's happening. Actually, sorry. Let me go again. See? I think it got a little bit more confusing than it had to be. So from here, we are now going to do minus 5n. See? So we do minus 5n. So minus 5 times 1, -1, and -1. See? Now really, it's going to be like you're adding both of these points, but now you're multiplying by a -5. See? That is a small detail that I should have mentioned earlier. You're still adding like the coordinates, it's just that now you're adding like in the other direction. See? So that is why you have a -5 here. So really you end up with 6, 8, 3 plus, okay, -5 because of this times this, plus 5 because of this times this, so just positive, right? And another positive 5. Okay, that makes a little bit more sense, see? And so from here, if you let these two interact just like before, you're going to end up with this 6 minus 5, so it gives you 1. This 8 plus 5, which is going to give you 13. And then finally, last but not least, you end up with this 3 plus 5, which gives you 8. And so the second vertex, vertex 2, okay, is going to be 1, 13, and 8. So really your last final answer is that this is the first vertex and this is the second vertex. And just for checking in the mark scheme, we do see over here that one of the vertexes is 1, 3, -2. Makes sense, that is this one right here. And 1, 13, 8, 1, 13, 8, it's right there, see? So you guys, this last part is definitely hard. I think that the biggest challenge is really understanding how to visualize it. And the biggest sort of thing you can take from this, like something that you might apply on like another exercise and stuff like that, is why you had to use the normal vector, okay? The IB loves to put like shapes and stuff like that in between all these vectors, and the normal vector, what it's essential for, which has to do with the word normal in this context, is that it's excellent for being a perpendicular line, okay? So perpendicular lines can be extremely important for getting stuff like heights, okay? So that is the biggest thing I can sort of let you guys know or write down for part E. Be very aware of how the normal vector really saves you in this exercise. All right. So you guys, part E was pretty wild, but part E was worth 7 points. So give yourself a pat on the back because that was very intense, even for me. And yeah, that is number 12. And that is actually the whole paper. So I hope it helped, and I'll see you around.